Hello and welcome to the KIM-1 Corner Part 6. In this episode, we'll be getting this UART card to talk directly to the KIM-1 monitor and run basic NAT through there because it will be faster. I'll be talking about the modifications that have to be made to the KIM-1 monitor to get it to run, and we won't be actually modifying the ROMs on the KIM-1 itself. We've got the memory card plugged in and there's ROMs on there, and we'll get it to boot direct to this new monitor, which will be the old monitor but with just the inputs and outputs redirected. Here we have a listing of the monitored ROMs for the KIM. Now this bit here, this is the first one. This is the 03 ROM, and this deals with all the audio tape stuff, so saving and loading that. So we won't be needing any of this. So all the code marked in yellow we can cut out and ignore. So that's all this bit, that's the whole ROM basically. So all we got to deal with is the 02 ROM. Now if we come down here, all the parts marked in green we'll be keeping. All the parts in yellow we'll be cutting out. And the blue bits is where I've had to modify stuff. We'll come to the modified code a bit later. But to start with, we start here at the beginning of the 02 ROM. Now we've got this section at the beginning called save. Oh, we can't really highlight it. This bit here is, I'm not sure what all of that doing. This part here, this is some sort of coming back in via the non-maskable interrupt or whatever. I'm going to leave it there because the code there and these bits down here is what makes the code start at C22. So will be FC22 will be coming in at this point here. It's 1C on the normal ROMs, but we're moving it up to the F range. That'd be FC22 will be the start. And these vectors here are, so these interrupt vectors, and they're hard coded at the top of the ROM as well. So we'll leave them as exactly as they are. There's one small change there, which we'll come to later. So first of all, the ROM sets up the user stack pointer. And then there'll be a bunch of code here for the new serial port. This is the original code that was there. This is all to do with reading the keyboard, testing which keyboard you've got, etc. First of all, it does initialization, which we don't need because that's the hardware initialization. And then it sort of scans bits on the keyboard that we won't have anymore. This is the keyboard actually on the KIM-1. Then we come into the start part. Now most of that we won't need, but there's a few bits here. When you very first start up on the teletype, or in this case a serial port, you'll get first of all carriage return line feed, and then the word KIM will come up. And we'll be keeping that bit to show it started up. And then it does this show command, which is to show you what address you're at and what data there is at that location. And it clears some data and then carries on, and it gets a character. It reads the keyboard. Now here we're reading whether you're on the teletype or the KIM-1 keyboard, so we don't need that. And this scan bit here, I've shuffled the code around in order a bit because it jumps around a bit in here, so I've reordered it slightly in the final version. But that's where it's scanning the keyboard and it will loop backwards and forwards. The next bit of code here is all about displaying on the KIM keyboard, so we don't need any of that because we won't be doing that all the way down to here. And then the code is jumping around a little bit, as I mentioned. We come to the load section. Now we'll go through this in a while, but this allows you to load and save to paper tape. Well, we can use this on the teletype or now as a serial port to actually push code on and off the KIM. So we've got exactly the same for the load thing. This is where you get a semicolon and then a byte telling you how many bytes are coming and then where to put it and then the actual code. So we'll keep all of that. Then there's the dump one, which is the opposite, where you'd actually be driving the punch tape. That's all the way down there, so we'll be keeping all that. And here we got show. This opens the memory address that you're sitting at and prints on the screen what data is in there in a hexadecimal format. So we'll be using that. And then there's this what the return key does. These bits of code here is what the scan does in a little while, which we'll get to. It's just have to remember this one's called space and show. And we've got one called return, and you've got go exec. Go exec is actually when you press the go button, this bit gets run. Loads up the stack with like return addresses, etc., and then does a return from interrupt. And I think that would been causing me a lot of problems in the next video. So if we come down to, remember back up here, we were going to, where are we? Right up here. Oh my goodness. This scan bit, which what I've done is that code down there, I've moved up to here, so I don't have to jump down to it, because this jumps down to the scan, then the scan jumps back up here. So I just brought the code up here. We just pop back down to the scan. So all that does is you've read a character in, and it then decides what is it. So if it's a space, then it's like pressing the space key when you've got the monitor open, and it just opens the cell that you're looking at, the memory address you're looking at, and displays the data. So if he sees a 20, it goes off and does space, which was this one here. So it opens a new cell and prints the data for it. If it wasn't that, if it was a rub out key, it does STV. This is to do with setting your baud rate when it's reading the actual bytes coming in when bit bashing. And then the next bit here, if you've got a return, you press the carriage return on the keyboard while you're in the monitor. It will increment the address that you're pointing at and then display the data. And if you do a line feed, which on the Windows you can do by doing Control-J, it will go back to the previous one. So you can step forwards with this one and step backwards with this one to show what data is in there. And then you've got a full stop for modifying, and this jumps to a subroutine called modify, which then alters the data within the cell you're looking at. So a cell is a memory address, basically, and the data that's in it. If you press G, you execute from the address you're actually looking at the moment. So when we're running Microsoft Basic, we put in there E065 and then space to jump to that cell when it's displaying it. If we then press G, it actually executes from that memory address onwards. And then you've got Q for dumping data. So you have to set up a couple of addresses. And this is for sending to the teletype. We just saw the dump routine earlier. And then load, that will just wait for data to come in from the teletype and stick it into memory, depending on what that file actually says. And it's a handy device. These two here, very handy for saving and loading to the terminal program. And then if it isn't any of them, then we just jump back to read, which is in this all the way back up to the top. There we go, back up here to read a character, get the character, pack it. The pack bit just turns a, if you've typed in 2 characters of ASCII text, it turns it into a number. So if you typed in 40, it will turn that into the number 64. We'll go back down to where we were, get scrolling here. Now you've got these bits here, which pulse me for a moment. But when you're doing commands, these commands here, they're jumping down to here. You've got so many different subroutines that this branch if equal command, it hasn't got enough range to reach the subroutines. So what we've done is that just branches down to here, and then this does a jump to the actual routine. So it has to do like a double skip to reach the actual code. And now it's all sort of subroutines. Feed means line feed. So that's this Control-J, which is, there we go, that one there. Previous cell. So if you press Control-J, you come down to here, and it decrements your memory address and then goes to show again to show what data is in there. So it just loops back again. Modify, that will actually load in the data you've got there and save it to that address. There we go, it's storing it there and returns back again. This is a useful one, point print. What that does is it prints the address of where you are. So it uses this print byte command. So it takes your address and converts it into hexadecimal ASCII on the screen so you can see the address. And then print string, this allows you to actually print a whole string that's saved in ROM. So you just put your pointer to it, so it's at a location called top is a table, and you just put an offset on that as to where your string starts. And it counts backwards through it, puts that string through the character out, so you can have saved strings and then just spit them out. So like that KIM at the beginning, that will just use this sort of thing. So carriage return line feed, you call this little routine, and location 7 is the top, so that'll be line feed, and then 6 will be carriage return, and then there's some nulls before that. So for some reason it sends out 6 nulls at the end of every string. You may remember when we had the Teraterm running, it kept putting those funny characters at the beginning. Well, that's where they're coming from here. That bit there should be in blue, because I'll change this later. There we go. This is useful, as I mentioned, this is the print bytes. This is where it gets your byte in A, and it chops up the top nibble and then prints it out as 0 to F, then takes the next nibble of it and does the same again. So it splits it in 2 and prints it out as like hex, but in ASCII. Now these are the main bits down here that we've got to alter. there's get character. So all this bit here is all about either reading the keyboard on the KIM or the teletype, which is bit bashed by the KIM. So we don't need any of this. All this delay for half a bit, etc. We haven't got to do any of that at all. So we've got a whole new block of code for there. And initialization of the I/O ports on the 6350s, we haven't got to do any of that. So we can scrub all that as well. There'll be a new initialization code. This is where we just print one character. You can do a space. So if you come in at this point, it puts the ASCII for base into the A register and prints it out. Or if you come in at this point here, you just have what character you want to print in the A register and it will print it. So we've got new code sitting here because that'll be the character out. So we haven't got to do any of this bit bashing again. So missing all this code out here. This is all half bits, etc. Don't need any of that. And this part here is increment the pointer. This just basically increments this point where if you increment the low byte, you've got to check whether you've had a carryover or not. If you have, then increment the higher one. So that's just a little routine that gets called in various places. Then there's get key from the keypad. You don't need any of that. Now get byte. This is similar. It's if you've typed in two characters, as I mentioned earlier, you typed in say a 4 and a 0. It gets those two characters and it joins them together and says, oh, that must be a number 64, and sticks it out again. Bit here is about setting up these pointers for actually opening a cell for reading, so we'll keep that bit. And then here's the table with all the code, etc. in it. So if you wanted to print the word KIM, you'd look at this address here, and your pointer's pointing here. Oh, how's this going to work? This is labelled in here a bit wrong. You actually start here and go KIM, carriage turn line feed 000000 as you're writing things. If you're doing error, it will be carriage turn line feed ERR, carriage turn line feed, and I guess it will stop there. Otherwise, you'll write KIM again. This bit here, these data bytes, this is for converting your hex into 7-segment displays. And then last of all, you got the reset vectors. These will be up at normally at 1 FFA. We'll be having them at FFFA. So these are just returning. So that's what's actually in the KIM ROMs at the moment. When we come down here, this is what I've created from that. So I've cut out all the green bits, put them in here, and then added some blue bits. Now this bit down here, I will be incorporating into the ROM that's got the basic on it, but this will run standalone. So all you'd have to do is take these bits off here where it says org to say where it's starting from and shove it through an assembler, and it will build it all, and you'll have a separate binary file that you can just put up in that top memory location and run that just as the monitor with nothing to do with basic at all. So here we go with the first bit that we said we'll keep there. This bit here was jump to subroutine inits. Well, we haven't got inits anymore. We've now got Initcomm, because inits was to set up the keyboard on the KIM. We're just using the comms port we've built, so that'd be slightly different. That's if that code ever gets called. And here's our interrupt vectors in the same place. So we actually start here. So this memory location should be 7FCC will be coming in here. And that's what's going to be put into the vector table at the top. So when we boot up, we come in here. It loads the location of the stack pointer, first of all. So it puts it into X and then transfers it to the stack. And then here's the new code. I had a lot of trouble with the system. With the next episode, we'll be bringing in a new board, and I was having a lot of problems with it when it turns out that the clear decimal flag was getting set on the processor at power up. And I still don't 100% know why. According to the manuals, it's totally random what it's set to, but the KIM itself always starts up properly with that cleared. It does say in the manual that you should clear this flag. Don't assume it's correct. So we've got here, clear the decimal flag, because if that's turned on, when you do an addition, it adds binary coded decimal rather than just binary, and makes this processor look like it can't add up. And all these offset tables, it starts jumping to the wrong place and causes all sorts of grief. So computed addresses don't work when that's turned on. So make sure that's turned off. Also here, if you was going to use the interrupts request built into the comms card, then you need your interrupts disabled to start with, because as soon as you initialize your comms card, it will initialize the interrupt to say that it's empty, and you'll get an interrupt and crash yourself out if you haven't set up the vectors already, which you won't have done at this point. So we make sure the interrupts are disabled. So here we've got Initcomm, where we're going to initialize the comms port. So we whiz down and look at that first. There we go. Initcomm. We come in here. Note that the compiler, the CC65 compiler, because it comes from the Linux world, is case sensitive. So if you put Initcomm in capitals and then try to point to it with lowercase, it won't find it. Or I found out this with a flag called data. I was going to completely the wrong place, and my carriage returns and that weren't printing carriage returns, and that puzzled me for quite a while. But it's because it's case sensitive, so watch out for that one. Back to initializing the comms card. First of all, it'll be in this mode. So we're loading these bits here, which said it to be 8 bits, no parity, 1.5 stop bits, and then the baud rate is set by the 555 on it, so we haven't got to touch that. So we store that on this hard-coded address here. So if you did put your comms card at a different address, you'd have to change this address here and reassemble this code. And then we load a 5 in there, and that is to turn on these bits. This is in the status mode now. And we turn on the receive part of the chip and the transmit part, and we just store that into the same location and then return. So that's all there is to the initialization of the comms port. We go back up to where we were. There we go. Initialize the comms port. So now you remember we had like load and save and things here. Well, I've shuffled things around so it flows a bit better. So here, this is the start of the code now. So we'll be keeping this. This is what we kept from the other one. Only modifications, I turned that to a 5 instead of it was an A, because it was doing KIM, carriage turn line feed, null. And it's getting all those funny characters on the screen. For well, we don't want that. We want it nice and clean. We don't have to send in null codes. I think that was just for the old-fashioned real teletypes. They might need it to keep the signal going for some reason. I'm not sure. So we just do a carriage return line feed to get us back to the cursor back to where we need it. So here we load 5 in, so we only load transmitting the 5 characters, which is KIM, carriage turn, line feed. We don't get all the nulls then. Then we immediately jump to this show one, which is show the address and the data that's in it. So that's the same as it always used to be. And then here we go, just going through the same usual stuff as before. So here is the bit of code I've brought up that was scanning the keyboard. It makes more sense being here. Instead of jumping to it and coming back, we'll just put the code here. Clear the buffers and read stuff in. So getting a character. And then what does that character mean? Whether it's a space key, then jump to that routine. If you've got a carriage return, jump to that routine, so forth. All the way through as we mentioned before. And I've added 2 new ones. Now, while I was having trouble with this bit being set on in the status register, I just thought I'll put a command in there just temporarily. I'll leave it there for the moment. Because if you press R, it prints the status register on the screen. So it's got this status register print little sequence that will run later. And also, I'll put in there, if you press M, it'll run basic. I could have used B for basic, but you could be typing in a hexadecimal code with the letter B in it, and it may well jump to it. Well, no, actually, it would jump to it, so we don't want that. So I'll put an M there, and that will jump straight to basic. So you don't have to type in the EO65 space and then G to go to it. You don't have to do any of that. Just press M and you'll jump straight to basic. Of course, if you don't want basic, just cut that bit out. So if you want to do the status register print, you jump to that bit of code here. And if you want to do the basic, you'll jump to the cold start vector within basic. So if ever the basic is modified and the cold start vector moves, it doesn't matter because it will be picked up here. So that was the previous line, left the same. This is the go command. Again, I'll put in here to make sure the decimal mode is turned off. This is pushing and shoving things around on the stack. And when you do this return from interrupt, it actually puts the status register from the stack back into the actual status register. And if that bit was ever set on, then you're going to end up adding binary coded decimal. So I'll try to make sure it's turned off there. I'm not sure how well that'll work, but that's just like a little safety net. And all the rest of the code the same. And there's the print bit for the status register. All that does is pushes the status register on the stack and then pops it back off into the A register and then prints it as hexadecimal on the screen. And then carriage turn line feed and bounces back again. So it just prints it on the screen so you can see what it is. It just be a hexadecimal number and you can work it out into the bits to see which flags are on and off. And all the rest is the same. So this is loading from paper tape the same, and dumping is the same because they just call vectors for getting and saving characters. So pretty much the same. Then we come down to carriage return line feed. That used to print carriage return line feed and 6 nulls. Now all we want is carriage return line feed, so it's just to swap the line out for this one instead. Just change that value basically from 7 to 1. And print bytes the same. Right, get character. This is the new code. It's all quite small here. So all we have to do is load in the status of the comms port, which is at 1501, hard-coded again, so if you're using a different address on your comms port, you'd have to change that. And then AND it with 2 to get the bits you want, and then compare to make it check whether it's a 2 is on or off, so that you set or reset your 0 flag, then branch depending on what it is. So if it's a 0, you bounce back if it's not ready. If it is ready, it'll be a 1, and you'll just carry on through to here. So this is just loop until your comms port is ready to read a key, as in some data has come in. Wait for the data. I wasn't sure whether I should have to wait or whether I should just check to see whether there was data or not. But looking back at the original code, it actually waits for a start bit. So it must be waiting for data to come in. So I'll wait for data to come in. When the data is ready, loads the A register with what's in the data port. So you echo what you just received back out again, so you can see what you've typed in. And when it's done that, it just returns back because the print character preserves the A register, so that's okay. So you just return with what you just read in the A character. And this is code we're keeping for printing things. So there's out space or out character. There's one out space and one out character. This is the vector name that's used within BASIC, and there's an in one as well. So here, if you're coming at this point here, you'd load a 20 into the A register, and then, which is space, and then print it. So that's just a quick call for printing a space without you having to load the A register. But the main one is this one here, out character or monitor out. So the first thing you do is save the A register into the character buffer. The reason beyond that is because the A register is going to get destroyed further down here. Before we can send the data, we have to check that the transmitter is ready to receive it. So read the status. This time it's bit 1 instead of bit 2. And if it's not ready, we'll branch back. If it is ready, we'll go forwards to here. Because this bit here has destroyed the A register, we now have to load the A register back in from the character buffer where we saved it, and then just put it out to the data address, and it will get sent. So we just return. So that's the whole transmit. There's no bit bashing or anything. It's a lot smaller. And here's some more subroutines that we've been through before, incrementing pointer, etc., and checksums. And then we come down to the data. These are the original null characters that were sent out. I just highlighted them. I just commented them out with a semicolon there so they're ignored. I don't normally delete code until I know it's not needed. So I just comment it out. And then here is your KIM and carriage return and error. And these bytes down here, these were pretty sure it's just those ones there are for the 7-segment display. So I'll probably delete those as well. It won't make any difference, just save a few more bytes in the ROM. Oh, and there's a few more there. There should be 16 of those, I think. Yeah, whichever. We could work them out. And that's the new monitor ROM. I've incorporated this all into the BASIC, so it's all in that compiler, so I don't have to keep redoing the pointers to the different characters in and characters out, etc. Okay, after that marathon, for those of you who are still here, we'll go through what needed to be done in the BASIC. This is a bit shorter. But these files here are the ones I had to modify to get the whole thing to compile with the BASIC. Not a lot really, but we'll go through this. So if we bring this over into the middle and open it up a bit. Let's see what we got here. I didn't have to change much in this. We've been through this before when creating the BASIC. All we've got to do here is you can take out these vectors down there. There's normally only 2 in here, these bottom 2 here, and I've redefined those in the actual monitor code. It's all tied in with this. We don't need them defined anymore. And this is where I was trying to get it to work. But these vectors kept changing. And I was getting annoyed having to keep going backwards and forwards. And so I thought I'd compile it all into one big group of files. Then we've got KIM extras. Come across this one before. This is where we've got those odd bytes at the top of the ROM. Don't know what they do, but they're still there. But I've put these 2 extra includes in there. One's the KIM monitor source and the other one is a KIM vector source. This is getting very much like the Benita version. His one's called Wasmon and some other stuff. I have relied heavily on things he said in his videos. Be sure to check out his YouTube site. He's got a website as well, I believe, on how the 6502 all works. And the next one is the KIM vectors. This is the actual vectors. So it includes this bit right at the end, and here's the vector that we'll be going to when we boot up, and the other two is the interrupt and non-maskable interrupt vectors. Now here we've got the KB9, which is KIM Basic 9. Why they couldn't call it KIM, I don't know, but that's what it's called. I had to do some editing in here to get things to go into the right places. Well, I've added these two new source files. One thing I did find is I'm wondering whether the 65 compiler has got a little quirk in it somewhere, because when it comes to this base ROM here, saying it's that size, if I then said the monitor is going to be sitting at that address, it wouldn't do it unless I actually backfilled this one here. I had to turn fill to yes rather than no to get it to fill the ROM all the way up to this address to make sure the monitor was put in the right place. And again, I had to put fill on that one to make sure the reset vector went into the right place. So I had to create these two new memory locations. And then just at the end of all the different segments, after the extra one, dummy one don't count, you put the KIM monitor and KIM vector there, and that's where it compiles the those two source files and pops them in there. Now the next one is the IscntrlC. The KIM monitor would like to read the actual onboard keyboard for stopping the basic from running, and that's this bit up here. And that's where it's reading the ports coming in for the keyboards. We don't really want to be reading it from there. We want to be able to just press Ctrl-C on the keyboard to stop the basic running. So that bit of code's blocked out, and we've got a new bit of code here. Now this bit of code actually sits right in the middle of another bit of code called flow1. There's actually an include file right in the middle of it, because this bit here, which says runs into stop, I thought, what's going on? What it is this bit of code is put just before the stop command, the basic stop command, which stops it from running. So if you do Ctrl-C, which gets scanned every so often, this bit of code runs and then carries on down to the stop command in basic. Again, we just, is there anything coming in at port, cons port? If, in this case, if there's nothing coming, then just return. Don't wait for a character. Is there one there? No, there isn't. Just return. Don't worry about it. If there is a character there, then load it in, see whether it's a 3 or not. And then you've got to look at this stop command to see what's going on further on. So that's in the flow1 source file. So what it basically does is says, if it's a 3, as in you press Ctrl-C, then do a stop, else just return. And then we've got inits, which is the very first bit that's run. We didn't have to change too much in this. Open up a bit. This is the first bit of code that's run. This is the cold start, starting in basic. First thing we do is clear the decimal flag, make sure that's cleared, otherwise it just can't add up. So we need that. That's one important bit there. And that is the actual monitor program, which we went through earlier, just now with all the green coloured coding on it. So now let's program the ROMs and stick them in the machine to see what happens. All we need to do is run the compiler as I've done before, and it compiles everything up and creates a new file which is now 16K long instead of the previous 9K, because we've got the monitor sitting at the top. And then all we've got to do is program it into an EEPROM. If we load the file up, there we go, it's a new one here. You can see it's 16K long. And that's all the basic sitting in there. And we program that into an IC, and then when you come to the second one, we can just put that as 2000 there, because they're 8K ROM chips. So this is the second one, so 2000 is actually 8K. And we could load that up for the second one, which is, this is the second half of the basic ROM. And then we got all those zeros where we had to fill it in with nothing in there. And here's the monitor starting at 1, it says 1C, it will actually be FCC when we're actually encoded. And at the bottom here, we've got our reset vectors. So just program them into the EEPROMs and plug them in. So here we have the KIM-1 with the expansion board plugged in. So all we've got to do now is plug in the ROMs. So here's the two new ROMs that we've got to put, I've programmed up and put in, and the RAM sitting in there. We just plug this in. Yeah, nice and snug in there. Now this lead is the comms from the new, let me bring that down a bit, from the new serial port we got. And we're still powered via the old port at the bottom. And this is the old serial port, well, teletype port. If we power this up, and we press the reset button, and see what we get on the screen. So if we start up Putty now, we want serial port, be on COM3, and we want to turn flow control off. Here we go, we bring that to the middle. Now we press a key, and there we go, we're in here. So P085 space, start looking at that one. Then we press that R key that I programmed. There we go, that's telling us that the status register's got a 37 in it, so you can work out what bits are on and off there. That's just for sorting out the problems in the next episode. So that's going. And if we just press M, we go straight into basic. A quick little program here. 10, print, I can't edit. 10, print, wrote, enter, and 20, go to 10, just list that to make sure it's okay. And now we do a run. And there we go, we're running. So Control-C. Come on, eventually get there. There we go, managed to break in at last. There we go, basics all working. Let's see if we can transfer a file. Let's run up Teraterm. I'll bring it in the middle. Serial, if you please. COM3. Yeah, that's the middle of the screen. And we've got to restore the setup, so we'll have that one. And also we need to put a line feed on that so we can see what we're doing. And just press a key. Oh, we're still in basic. Let's quit out of that, reset it. Okay, there we go. So if we press L for load and do send a file. I've got one all ready to go, tucked away somewhere. That one there. This is like tiny basic, but it's in a PTP full. Doesn't matter which one it is. So that's 6K long. And we put a delay per character to give the KIM time to do the checksums, etc., and save the data in the right place. And it's got to convert the data coming in into decimal. It's all in ASCII at the moment. So okay, and there it all comes in, and that will keep flowing until it's finished. We'll speed this bit up. There we are, all loaded. So if we look at, let's look at the first line on this. We scroll up. First line here, there's your semicolon to say, here's some data coming in. And then 18 is decimal for 24, so it's 24 bytes. And it says starting at address 2000. And then we'll start loading in. So the first character loaded in number should be 4C. It loading all these bytes until it gets to the last two there, and these two here are the checksum. So that would be 08BF is the checksum, but this is all sent in ASCII. But so we're looking for 4C at address 2000. So we go all the way to the bottom. We go to address 2000 space. There's the 4C. So we can see it's all been loaded in there, and that's all the codes 4C85, so forth. We can use that for loading in, and you can do the same with Q. You just have to set up where you want to save data to and from. So the terminal's all working. We actually go back to the main camera here. There's the KIM sitting here. What I'll do is I'll turn it off. I'll pull the power supply and take this edge connector off the bottom. I'll then use this other lead from one of the other cards, and I'll plug it on that power connector on the back of the daughter board. Plug the supply back in, make sure I've got polarity around the right way. Yep. And power it on again. Press reset. And if we quickly flick over to the other display, we're running again. There we go. We don't need this edge connector that fits on the bottom down there. Obviously we lose the onboard serial port, but we're not using that now in here. We're using the other one, which is faster. We only got one board plugged in the KIM at the top here, and we don't need anything in the one at the bottom. So we could put something else on there if we wanted, or we just leave it blank. We're all standalone at the top. So sorry for the long video there, but I couldn't see any way of making it any shorter. But the next episode will be a bit more interesting. We will be introducing this card. If you want to find out what it is, be sure to tune in for the next episode. And don't forget to like and subscribe and put lots of comments below so it helps the YouTube algorithm. So see you in the next video.